Hi everyone, let us discuss this example of norm. Okay, in this example they have given a set x. So see how they have defined x. X is nothing but C close interval 0 1. C stands for set of all continuous function, right? And close interval 0 1, that means functions which are continuous on close interval 0 1. That means if I draw the diagram, it will look like this 0 1. So if any function f, okay, it's continuous on close interval 0 1, then it will be a member of this set x. Okay, so we are talking about functions, getting the point? Okay, and they have defined a norm in a form of integration. You can easily see here. So they have defined a norm with the help of integration 0 to 1, and after that they have written mod f of t dt. Okay, so now we have to prove that it is a norm on x, right? So tell me how to prove that norm on x. It should satisfy how many conditions? 4 conditions. First condition, it should be greater than or equal to 0. Second, is equal to 0 if and only if that f or x will be 0. Third condition, if there is any alpha, you should able to take it outside, but mod will carry when you take it outside. And the last condition, if you take a separate norm, value will get increased. So let us discuss this example and we will check the given function is a norm on x or not. Okay, so I will simply mention we have x is equal to C close interval 0 1, right? And norm is also defined, and I will mention and for f belongs to x, so norm 1 is defined as integration 0 to 1, right? Integration 0 to 1 mod f of t dt. This is my 1. Okay, so let us check all conditions. So the first condition I'm going to check, for f belongs to C close interval 0 to 1, which is our x. So if you take any member of x, what will happen? Clearly, okay, one thing we can write directly, that mod f of t is greater than or equal to 0, and this is true for all t belongs to close interval 0 1. So you know that when we take a mod, no need to worry about negative sign getting, so mod cannot be negative, so that's why it is greater than or equal to 0, 101% true. See, if the function is non-negative and if you take its integration, obviously the value of integration is also non-negative, that means greater than or equal to 0. But this is nothing but definition of norm 1. So therefore I can write this is definition of what? Norm 1. So f1, which is greater than or equal to 0, and this is true for each f belongs to x. Since we had chosen any arbitrary f and it is true for f, so that's why it is true for all elements of x. So in this way we prove the first property. So let us try to prove the second property. What is the second property? So as you know, in second property we start with norm f1 is equal to 0. In second property we equate it with 0, and finally we have to prove that f is also equal to 0. Okay, so let us start to do if and only if. So I will use the definition of norm 1. What is definition of norm 1? It is written here, integration 0 to 1 mod f of t dt is equal to 0. Okay, so simply I wrote the definition. See, what is meaning of integration? Actually the meaning of definite integral is area under the curve. So if you have 0 to 1, if you have a function like this, then integration gives the area under the curve. See, function is mod is there, that's why it cannot be negative, so it will above the x-axis, getting the point? See, if the function is negative, that means some part will lie in a negative part of y-axis, getting? So but see, function is positive, no, that means non-negative, so that's why obviously it will lie above the x-axis, and the area is 0, that means obviously the function should be 0. So this is the only possibility we have, so that's why mod f of t is equal to 0, and this is true for all t belongs to close interval 0 1, right? If and only if. You know that when we have a mod is equal to 0, if the whatever inside mod it is 0, then only mod will be 0. So that's why f of t will be 0 for all t belongs to close interval 0 1, right? So function is 0 on this interval, so simply we can say this is 0 function, okay, on close interval 0. And that means we started with norm of f is 0 and finally we got f is also equal to 0. So that means in this way we proved our second property also. After that we are going to prove the third property. Make a screenshot of it and after that we will go further. Okay, so let us continue. This is our third property. In third property we want alpha. Alpha I have taken. We want f. F I have taken. Okay, and we start with norm alpha f. So finally, we should able to take that alpha outside with a mod. Then we can say the third property will be satisfied. So let us start to do. This is equal to, see, let us see what our definition says. Our definition tells us that we have to take its integration. So let us take its integration. Integration 0 to 1 f. Okay, we have a alpha f. Alpha f of t, mod is there, right? And dt. This is equal to integration 0 to 1. So when you operate it on t, getting alpha is a constant, it cannot apply. Simply we have to apply f. So alpha f of t dt. So multiplication is there, that means we can take separate mod. So therefore integration 0 to 1 mod alpha mod f of t dt, right? See, but mod alpha is constant, and when you take an integration, as you know, in case of integration always we take constants outside. So here mod alpha is constant, so we can take it outside. So this is equal to mod alpha integration 0 to 1 mod f of t dt. So this is equal to mod alpha I copied. Okay, so do you remember this one? This is nothing but our definition of norm 1. So therefore this is norm f1. So in this way we started with this one and finally we could take mod alpha outside. So in this way we proved the third property. Okay, make a screenshot of it and after that we'll go for our last, that means fourth property, please. Okay, so let us go for last property. Okay, so for last property we require two functions. So I have taken two functions here, and what we have to prove actually. So simply I will mention norm x plus y less than or equal to norm x plus norm y. I hope you have understood what we have to do here. Here we have a functions instead of x and y. So that's why I've taken f and g, two functions we have, and finally we should able to prove this is less than or equal to norm f plus norm g. Instead of norm we will write norm 1 since symbol is norm 1 is there. Okay, so let us go further. What will I do? I will apply the definition. So definition says this is equal to, definition involves integration. So integration 0 to 1, right? Mod f plus g, we have f plus g of t dt. Okay, so this is equal to, so next step is obviously f and g will operate on t. So this is f of t plus g of t dt. So you know when we take a separate mod, value will get increased. So that's why the reason is mod a plus b less than or equal to mod a plus mod b. So this is a thing, basic thing we have. So this is less than or equal to integration 0 to 1. I can write here mod f of t plus mod g of t dt. Okay, so when we have an addition, you can take, you know that in case of integration we can take separate integration. So this is equal to, I can write integration 0 to 1 mod f of t dt plus integration 0 to 1 mod g of t dt, right? Simply separate integration we have taken, but this is nothing but definition of norm 1. So this is norm f1 and this is nothing but definition of norm 1 again, but here we have a function g, so that's why I'm writing norm g1. So therefore, okay, therefore I'm concluding now. Therefore we started with norm f plus g and less than or equal to we have got here, and finally we have got this is norm f1 plus norm g1, right? Yeah, so in this way all properties are satisfied. So that's why we can declare, I will write in this way. Therefore norm 1 is norm on x, since all four properties are satisfied. Make a screenshot of it and after that we will stop. Thank you.